Hey guys, welcome back. I'm Mr. Kim. I'm going over the question number 7 from the 2025 AP Chemistry FRQ. Answer the following questions about the glycolate ion, which acts as a base in aqueous solution. Lewis diagram for the ion is provided. So that's something that we need to pay attention to. It acts as a base, and we know that a Bronsted definition of base is a proton acceptor, right? So it's a proton acceptor. On the Lewis diagram, part A, circle the atom that accepts the proton when the glycolate ion reacts with water. Well, you don't have to know this. I don't cover a lot of organic chemistry or into depth in my AP classes because it's such a small part of it. Also, if you take a real intro survey chemistry course in college, organic's not really part of it. But you don't have to know that, but if you take in bio or AP bio or some sort of a bio, you should understand or recognize this portion, which is what? Which is this, right? So what else we know? Well, first of all, we know that it's kind of difficult for the proton to come in and attach to these 2 points, right? Essentially, in the end, what happens? This is the oxygen with the most number of lone pairs, right? So essentially, the proton is going to make a connection over here. So your answer is going to be, let's erase this, right? It's going to be right over here like that, okay? And that's the correct answer for part A. Let's move on. When the glycolate ion reacts with water, it forms glycolic acid. According to the following equation, the Kb expression for the reaction is provided. How nice. At 25 degrees centigrade, a 2.5 molar solution of glycolate is found to have a hydroxide concentration of such. Calculate the Kb for the glycolate ion, right? So, because of the lack of space, I should have thought about it. I'm going to rewrite the equation, right? Like that. Right? So, unnecessary on your part. I'm just doing it here for explanation, right? So you're looking at your ice chart, and what do we notice? It's a 2.5 molar solution of glycolate, which means that we start with 2.5 molar solution over here, right? What about water? Who cares about water, right? Because it's not part of our expression, right? And then what do we got over here? Well, we end up with, start with none of these, right? You might be tempted to stick it in the hydroxide side, but that's not what it is. This is not a common ion in this case, right? How do we know? How do we know to put it in here, the this value? Well, you would put this in here if the problem said something to the effect of a different salt was dissolved at this concentration, but that's not what's happening. It's what is happening is that you have this and it's found to have a hydroxide concentration in the solution of this. That is why we know that this value gets written down here at equilibrium. Okay. And what do we know? It is a balanced equation. It's a 1-to-1 stoichiometric ratio for all. So then that means that you're going to end up, right, just like this. And what do we know? These two values came from here, from getting created, right? And what happened? This came from the fact that the change was like that, right? So I'm going to have to erase this part because there's no space, right? But what do we know? This value is going to be 2.5 minus 1.3 times 10 to the minus 5. Now, does that make a big difference? The answer is no, because this is such a small value that the number is not going to deflect much from 2.5. But nevertheless, I'm going to stick it in because I have the number. So what do? The next thing is we got KB, right? We have the expression right up here. So we know it's going to be 1.3 times 10 to the minus 5 squared all over 2.5 minus 1.3 times 10 to the minus 5, right? And that value should come out to 6.8 times 10 to the minus 11, I think. So 6.8 times 10 to the minus 11, right? And that's our answer. Part 2, using your answer to part B, calculate the value of Ka for glycolic acid at 25 degrees centigrade. You know that 25 degrees centigrade, our maximum pH value is 14, or our Kw value is going to be 1 times 10 to the minus 14. All right, so at this, so essentially at this, our Kw is going to be 1 times 10 to the minus 14. And you know that this deviates as the temperature changes. But in AP, unless they tell you, it's almost always going to be at Kw of 1 times 10 to the minus 14. How are they related? We know that Ka, or the product of Ka and Kb in a solution, is equal to our Kw. So our work's going to be what? It's going to be to calculate your Ka is going to be Kw divided by Kb, which in this case is 1 times 10 to the minus 14, divided by our 6.8 times 10 to the minus 11. And that should render us a value of, not sure, did I do the math on this? Yes, I did. It's going to be 1.5 times 10 to the minus 4. So I'm going to go over here and write that down. Ka equals 1.5 times 10 to the minus 4. Easy enough, right? Let's finish this off, right? So part C, a student claims that the hydroxide, well, I'm sorry, let's read the whole thing, right? Glycolic acid can be produced from the hydrolysis of methyl glycolate. A proposed mechanism for the reaction is given. And it says a student claims that the hydronium is a catalyst for the reaction. Let's go take a look at where hydronium is located. I see one right here. I see one right here. And that's it. Do you agree or disagree? Justify your answer based on mechanisms given. What do we notice, right? The person says it's a catalyst, right? So what do we know about catalyst? Catalyst is something that let's go through it. Catalyst is something that lowers activation energy, provides alternate pathway, right? But what else? In terms of reaction mechanisms, we understand that catalysts are used up in one step and it's recreated in a subsequent step, right? So do you see that happening here? And the answer is yes, right? Hydronium is actually spent, and it's a reactant on step A, and it disappears. And in the step 2, it is recreated, so it looks like it never left, right? Whereas enzymes, or not enzymes, the whereas intermediates are backwards, right? Intermediates are created in one step and it's spent in the subsequent step, right? So essentially, in the end, the student's claim is actually correct, right? So I'm gonna write that I agree with the student. Justification is that you notice that hydronium is used up in step 1, but it is recreated in step 2, a subsequent step. This is the definition of a catalyst. Okay, so that concludes the question number 7. I hope this was helpful, and thank you for watching.